In this video, we're going to talk about permutations and probability. We know that from the multiplication rule for probability, that the probability that A occurs and B occurs is equal to the probability that A occurs times the probability that B occurs, given the knowledge that A has already occurred. We also know that when all simple events are equally likely, the probability of an event E is the number of simple events in which E occurs divided by the total number of simple events possible in the experiment. So we do want to know how to count the number of ways that something can occur in general. And so we're going to talk about this multiplication rule for counting in general as well as just in terms of probability. So the multiplication rule for counting, very similar. If event A can occur in n ways and event B can occur in m ways, then the number of ways that the two events can occur together, the number of ways that A and B can occur is equal to the number of ways that A can occur times the number of ways that B can occur. So that's n times m in our example. And just like we have to think about, the conditional probability of B given A in circumstances where A and B are not independent, this is with knowledge that A has occurred. So for example, if you're taking cards out of a deck without replacement, you need to, after the first card is taken out, take into account that first card is taken out when thinking about the number of ways that the second card can be taken or selected. So as just a basic example, if you roll a die and toss a coin, in how many ways can the die and coin be rolled and tossed? How many outcomes are possible? Well, this was a 6-sided die and presumably a 2-sided coin. There are 12 different possible outcomes for that die and that coin. Here's another example. There are 7 people in a race. If ties are not possible, how many different orders can the runners finish in? So for the first person, there are 7 possibilities for who gets in first place. There are 6 possibilities for who gets in second place. There are 5 possibilities for who gets in third place, and so on for each of those places until we get to absolute last 7th place, and there's only one person remaining who could come in that 7th place. So 7 times 6 times 5 times 4 times 3 times 2 times 1 is the number of different possible orders that those runners could finish in. And again, we're using the multiplication rule and the fact that because somebody came in 7th place, that person can no longer come in somebody came in first place, that person can no longer come in second place. So there are 6 possibilities left for second place and so on. Doing a multiplication like this of an integer, a positive integer, and then all positive integers less than it multiplied together is common, and therefore it has a special symbol and name. So this is 7 factorial. 7 factorial. And in general, it's the case that n factorial is equal to n times n minus 1 times ... down to n. So n factorial, for a positive integer n, is equal to n times each positive integer less than it. So as one more basic example, 3 factorial, for example, would be 3 times 2 times 1, that's 6. And a kind of funny definition is that 0 factorial is equal to 1. The reason that 0 factorial is equal to 1 is because 1 is the multiplicative identity. So if you multiply 0 times nothing, this is sort of our reason for 0 factorial being defined as being equal to 1 as opposed to 0. So let's look at a similar question. If there are 7 people in a race and ties are not possible, how many possibilities are there for the number of ways that the first, second, and third place runners can come in? So try thinking about this in two different ways. Try to write this using the multiplication rule, and then also try to write this using factorials. So I will pause and you can think about it for a moment. Okay, so using the multiplication rule, we're only interested in the first, second, and third place winners. So those are the only ones we're interested in. How many ways are there for the first place winner to come in? There are 7 ways for that first place winner to come in, and there are 6 people remaining who could be the second place winner, and there are 5 people remaining who could come in third place. So using the multiplication rule, we can just multiply those numbers together. 6 times 5 is 30, times 7 is 21, 210. So 210 ways for that to occur. Using factorials, okay, so we know that 7 factorial is the number of ways for these 7 runners to come in. 7 times 6 times 5 times 4 times 3 times 2 times 1. So that's 7 factorial, and that's kind of close to what we have over there, but not exactly, right? So there's this stuff that's extra, and this 4 times 3 times 2 times 1 is extra. So what does that correspond to? That corresponds to our fourth, third, second, our 4th, 5th, 6th, and 7th place winners that we don't care about. So we could think about this as sort of modding out by those places we don't care about, dividing by 4 times 3 times 2 times 1. In other words, dividing by 4 factorial, because there are 4 place values whose rearrangements, whose orders we do not care about. So this 7 factorial over 4 factorial, that's equal to 7 permute 4. And in general, n permute k is the number of permutations of k objects out of n objects. And this is the number of ways to select k objects from n objects, where the object can't be repeated and the order in which the objects are selected matters. So P n k is also written as n permute k, and that's n factorial divided by n minus k factorial. So basically we're talking about the number of ways to rearrange these objects, but we don't care about n minus k of them. We only care about the rearrangements of the k of them. So n factorial divided by n minus k factorial is the number of ways to arrange k objects out of n objects, again, where we can't repeat an object. Just like above, first, second, and third place winners, there are no ties. So once somebody's already chosen in first place, they can't also be selected for second place. So the object can't be repeated, and the order in which the objects are selected matters. So again, we're distinguishing between first, second, and third place. So that's signifying that order matters. So a classic example of a permutation would be the following. A club of 15 students is voting on a president, a vice president, a secretary, and a treasurer. In how many ways can these positions be filled? So we've got our president, our vice president, our secretary, and our treasurer. In how many ways can these positions be filled? There are 15 possibilities for president, there are 14 possibilities for vice president, there are 13 for secretary, and there are 12 for treasurer. So multiplying those values together will give the number of different ways that can occur, so more than 1,000. And if we wanted to write this using permutations, 15 permute 4, that would be equal to 15 factorial divided by 15 minus 4 factorial, or 15 factorial divided by 11 factorial. And these two things are equal, and it can be good to continue thinking of this as the multiplication rule as opposed to a permutation, or continue to think of them both simultaneously. I think that this has more intuition around it using the multiplication rule, but this can be useful particularly if we're trying to find a general formula for something, and write that general formula in a concise way. So for example, if you were talking about the number of ways to select 300 objects out of 1,000 objects, we wouldn't have to want to write like this all out. We wouldn't want to have to write out, 300 numbers in descending order multiplied together. It is convenient to have a formula like this. So I'm going to go through a few examples together, and in these examples, some of these use permutations, and some of them do not. So do keep in mind the different rules for probability we have, the multiplication rule, and so on, and think about which of these problems do use permutations and which don't. So here are two examples to start that are kind of similar but not exactly the same. First, a door code requires 4 digits, 0 through 9, to be entered in a specific order. So for example, if the door code is 3579, then 7953 won't get you in. What is the probability that a randomly selected sequence of 4 numbers is the right code? So that's the first example. Example 2, that's similar but not exactly the same. A door code requires 4 digits to be entered in a specific order. You remember that your friend's door code didn't have any repeated numbers in it. What is the probability that a randomly selected sequence of 4 numbers with no numbers repeated is the right code? So grab a piece of paper, pause, and try those out. We'll talk about them in just a moment. Okay, so door code requires 4 digits to be entered in a specific order. What is the probability that a randomly selected sequence of 4 numbers is the right door code? So we're talking about one particular sequence out of the number of possible codes. So that's going to be our probability of the event that we're interested in. So what we need to figure out is what's the number of possible door codes. So the number of possible codes, this is the number of ways to enter 4 digits, 1, 2, 3, 4. And we know by the multiplication rule that that's the number of different possibilities for the first digit. So 0 through 9, that's 10 different digits, times the number of ways to enter the second digit. How many are there? Well, we don't have the restriction that we do in the second problem. So in the second problem, it says that there are no repeated numbers. But here we don't have that restriction, so we still have 10 possibilities for our second value as well, for our second entry in the door code. And we also have 10 possibilities for the third one and 10 possibilities for the fourth one. So that means that there are 10 times 10, 100, 1,000, 10,000 different possibilities for this door code. And so this is 1 out of 10,000. So note this was not a permutation. This was not 10 permute 4. And why wasn't it? This was because repeats are allowed in this case. We can repeat a digit. For example, the door code could theoretically be 4466. That would be a valid door code because we're not given any information that it is not. So repeated digits are allowed, we assume, and so this is not a permutation. This is just using the multiplication rule. All right, let's compare that with this variation. So here we said that you know something about your friend's door code. You remember that it doesn't have any repeated numbers in it. What is the probability that a randomly selected sequence of 4 numbers with no numbers repeated is the right door code? So again, it's still going to be 1 out of the number of codes, but now it's the number of codes with no repeated numbers. So how many of those are there? So a permutation has 2 requirements. N permute k is number of ways to select n objects from k objects where order matters and there are no repeated digits, or no repetitions allowed in general. No repeats, no repetitions allowed in general. So is that the situation we're in? Yes, they're entered in a specific order, so the order matters. The code doesn't have any repeated digits in it. So great, we are in the world of permutations. So the number of codes with no repeated digits is going to be equal to, well, there are 10 possibilities for the first code, 9 possibilities for the second, 8 possibilities for the third, and 7 possibilities for the fourth. Or this is the same thing as 10 permute 4, which is 10 factorial over 10 minus 4 factorial, or 10 factorial over 6 factorial. So we could, again, either answer that using the multiplication rule or using a permutation. And so the probability that you have that this is the correct code, so the probability that this one sequence of numbers is the right code, is still pretty small. It's 1 over 10 times 9 times 7 times 10 times 9 times 8 times 7 is our probability. So it's a slightly larger probability than above, but still fairly small. Let's look at 2 more examples. So first, there are 5 gerbils in a race to the end of the living room. You bet that one of the gerbils will get to the end of the living room first, with no knowledge of the skills of the individual gerbils. What is the probability that your gerbil will finish the race first? And second example, there are 5 gerbils in a race to get to the end of the living room. Allie, Bill, Cece, Doodle, and Ellie. With no knowledge of the skills and strength of the individual gerbils, what is the probability that Cece will come in first, Bill will come in third, and Doodle will come in last? So give each of those a try. All right, so with our 5 gerbils, what is the probability that a particular gerbil will finish the race first? Your intuition might just be 1 out of 5, and that is correct. You don't really need permutations for this, but if you wish, you could think of this as being equal to, well, there's one particular gerbil you're interested in coming first out of the number of ways for out of 5 gerbils to select one to come in first place, 5 permute 1, and so that's 1 over 5 factorial divided by 5 minus 4 factorial, divided by, divide 1 over 5 factorial divided by 5 minus 1 factorial, sorry about that. So that's 1 over 5 factorial divided by 4 factorial. 5 factorial over 4 factorial is just simply 5, 1/5. So we certainly did not need permutations in thinking about that problem, but there it is if you want to use them. Second, there are 5 gerbils in a race to the end of the living room. With no knowledge about the particular gerbils, again, what is the probability that a particular one will come in first, a particular one will come in second, and a particular one will come in last? So again, we're talking about one ordering. So, CC coming in first, and Bill coming in third, and Doodle coming in last. There's only one way for this particular sequence of events to occur. If we're just thinking about those 3 gerbils, divided by, now we could also think about this as 5 permute 3. So we're only thinking about who comes in first, and there are 5 possibilities for that, and who comes in third, there are 4 possibilities remaining for that, and who comes in fifth, there are 3 possibilities remaining for that. So that is in fact equal to 1 over 5 permute 3, 5 factorial over 5 minus 3 factorial. That's 1 over 5 factorial divided by 2 factorial. That's the same thing as 1 over 5 times 4 times 3. And so that would be 5 times 4 is 20, times 3 is 60. That's 1 out of 60 is our probability of that event.